Hello everybody, in this video we will be discussing Vernier calipers. So I have discussed this topic very crystal clear, making clear the principle how the Vernier caliper actually works, discussing all the formulae and finally practicing some good numericals. Okay, so do watch the video till end so you will not miss out anything. So let's discuss some major parts of Vernier caliper first. So first one is a main scale. You can use MS for it, short form. Second is vernier scale VS, and third one is a metallic strip used for measuring depth. So let's discuss them one by one. I'll just show you. Okay, so here if you can see the scale, which is 150 millimeters long or 15 centimeters, this scale, it's entirely over this metallic plate. So this is the main scale. I hope you can see that. If I bring it closer, the camera will lose focus. Okay, so this is the scale, metallic scale. It's over the entire length. Even you can see it whole till 150 millimeters. Okay, so it's over the entire length. It's called the main scale. Now what is vernier scale? Now vernier scale is missing in this caliper since it's a digital one. So in this place, in place of the digital piece, you will have another scale which is called the vernier scale. It looks somewhat like this, and just how the digital piece is moving over the main scale, behind metallic plate has a main scale, so this digital piece is moving over it. In the same manner, the vernier scale will move over the entire length of the main scale. Okay, so it just replaces this digital piece, and it's just basically a scale. Okay, so it can move. It's a movable scale, that is what. And here is that metallic strip which I was speaking about. So it's usually used for measuring depths. Suppose if you want to measure the depth of this cup, so you can't use this to measure depth. You can't go it this way, neither can you go this way. This is used for internal radiuses like this. Okay, this is used for outer dimensions like width, length. You fix it, you stuff things between the cloth, and then you get the reading over here. In your case, you will have some formula to calculate it. I'm getting ready-made answers due to digital vernier caliper, and this is the way you measure depth. So this metallic strip, the third one, is used for measuring depth. Okay, so yeah, we'll discuss now deeply how the principle, okay, how does the vernier caliper works. So quickly note down the parts, the major parts rather. It also has some claws, like if you see this claw is fixed, this one is fixed, this one is fixed. Now this is movable, so you can fit in stuff in there and then use your formulas, which I'll be sharing just soon, and then calculate the lengths. Okay, so I hope you noted that down. So what we'll do now is we'll choose a typical vernier caliper and derive some general results. We are choosing a typical vernier caliper, like it will have some features. I'll state those down, and we'll derive some general results which will be true for all vernier caliper. Okay, so the first assumption or the feature of our vernier caliper that we are choosing is MSD. No cricket, we are speaking of vernier caliper. Okay, so MSD is greater than VSD. What does this mean? So main scale division, so I'll put one main scale division is greater than one vernier scale division. So this is one main scale division. Okay, there are 10 actually, so this is one, this is one, this is one, so on till 10. Okay, so this one is greater than this. One main scale division is greater than one vernier scale division. You can see that this is a little bit less than the main scale division. So that is our first assumption, and for this lecture we will be strictly following it, it will be actually 99% of the times in your question, this will be the case, that main scale division is greater than the Vernier scale division. It will be true for 99% of the times, because I have seen one question. I'm not sure whether it was Olympiad or IIT Advanced, so I say it's safely as 99% of the time. So anyways, for today's lecture, it will be 100% of the time. So that is the first assumption. Second assumption that we are choosing, or the feature of our Vernier caliper, is one main scale division is 1 millimeter. What did we choose? That this one main scale division, each of this 1 main scale division is 1 millimeter. So each of this is 1 millimeter, 1 millimeter, 1 millimeter. Okay, so totally they are 10. So this is 10 millimeters. Till here it's 10 millimeter. Anyways, don't worry. So each one of them is 1 millimeter. That is our second feature of uh, our Vernier caliper. And now the final feature that we are choosing is, look here. So we have 10 VSD, so 10 of them are there, and this is ninth one now. So 9 main scale divisions is equal to 10 Vernier scale division. I know we are choosing a really particular one, but we are going to derive general results. Okay, so these are the three features of our Vernier caliper. So what does this has to say? Okay, what if we wanted 1 VSD? So 1 Vernier scale division is how much? Okay, so you do it 9 by 10. 9 by 10 MSD. Okay, it's 0.9. But what is MSD? One main scale division is 1 millimeter. So we can write it as millimeter. Okay, I replace this. You can also write it this way. 1 won't make any difference. So 1 main scale division is 1 millimeter. I replaced that over here. So 1 Vernier scale division is 0.9 millimeter. So this is the thing that we get from the third point, the third feature. So now we know that the first one, this interval is 1 millimeter, this division is 1 millimeter, this is 0.9 millimeters, each of them, this is 0.9, 0.9, 0.9, and here it's 1, 1, 1, 1 millimeters. Okay, so what if I ask you for the least count? For those who don't know what a least count is, I'll just briefly define it. It's the smallest value your instrument can measure. Smallest value your instrument can measure. So you might be tempted to say it as 0.9, right? This is 1 millimeter, this is 0.9, 0.9 is less. So maybe it is the minimum distance that it can measure. But wait a second, okay? So what if I stuff in something? Now we have to stuff in something to measure, right? Stuff in between the claws and then you'll get some reading, okay? So I stuffed in something. The thing what happened is this moved this way. Okay, it moves. This scale is movable. Vernier scale is movable. So it shifted a bit, and it shifted in such a way that this and this came in line. Okay, this main scale division first one and this Vernier scale division first one came in line. They shifted. Others also shifted, but focus on the first one. Okay, it shifted. It shifted. So can you tell me what was the distance it shifted? This is 1, this is 0.9. Maybe the difference between the two is the answer. And if you say that, it's absolutely correct. Because see, this is 1. And if you subtract 0.9 from 1, you will get the difference between them, which is 0.1. And that was the difference, distance it shifted. When you stuff that thing, it shifted that much. Okay. So that was the distance it shifted, and this value seems to be smaller than both of those, right? But let's go for one more case. Let's go for the second one. Now we removed that thing and stuffed a different thing, and what happened was it shifted this much. Okay, the second division came in line with the second main scale division. The second Vernier scale division came in line with the second main scale division. So can you tell me this distance now? Okay, what is the distance now? Okay, so this is 0.1. So the remaining will be 0.8 because the total is 0.9. So this remaining distance over here is 0.8 millimeters. Okay, this is 0.8, remaining distance is 0.8. Now look from here to here. Okay, this is 1 millimeters and this is 0.8. This is 1, this is 0.8. So the remaining is 0.2, which was the shifted distance. Okay, so it's 0.2 millimeters. Now you can note the pattern. Now it's easy. Now for first one it was 0.1, for second it was 0.2, for third one of the main scale and third one of the vernier scale will be 0.3 millimeters, and this goes on, right? And finally we'll have, okay, for the ninth one it will be 0.9 millimeters, and finally it will be 0.9, and it will be finally 1 millimeter. So 0.9 and finally 10, so 1 millimeter. Okay, 0.1 for 1, 0.2 for 2, 0.3 for 3, 0.9 for 9, and finally 1 millimeter for, finally it's 1 millimeter. So that was the reason it shifted from the 10th division to the 9th. So this distance is 1 millimeter. This is the distance between the 10th of the main scale and 10th of the vernier scale. But what is important here was the least count. I asked you the question, what is the least that you can measure on your instrument? So now can you tell me that? Okay, is it 1 millimeter? No sir. Is it 0.9? Seems, but no. See, the minimum is 1 among this, and which one is it? 0.1. So 0.1 is the least count of the vernier caliper that we chose, but we said we will state general results. Okay, so what can we say? How did 0.1 came? What did we do? We took the main scale, one main scale division, and subtracted it from one vernier scale division, and that gave rise to 0.1, right? Main scale division, one main scale division minus one vernier scale division. Even if you do that over here, this is 1 millimeter, this is 0.9, same answer, 0.1. So least count is 1 MSD minus 1 vernier scale division. Okay, so note it down, and this is absolutely correct for any vernier caliper which holds this. Okay, only this condition, if it holds, this is correct. Okay, and for today's class it's 100% correct. I'll release one question which has VSD greater than MSD on the website. You can then check it out and try to crack it there. Okay, so we found the least count, the least that our instrument can measure. What next shall we go for is the measurement, because we want to measure things, right? So what will be the measurement? Can I clean some things up? I'll clean the top. If you want to note, you can. Okay, so these were the features. Okay, this is true for every of the things that we discussed today, every of the vernier caliper that we discussed today. Okay, so now comes measuring. Okay, so measurement, final reading, what we want. So before that, come over here. Yeah, so what can we write 0.2 as? Can we write it as 2 into 0.1? Why sir, why? Okay, just write it for now. 3 into 0.1, 0.3, we can write it that way. What we can write 0.9 as is 9 into 0.1. Okay, and finally 1 millimeter also we can write as 10 into 0.1. So the division which is matching, so this had shifted 0.2, so 2 into 0.1, which is the least count. So I am finding a way to generalize the stuff. Okay, So this is the list count itself. So 2 into list count, the digit which is matching, the division which is matching into list count, division which is matching, suppose it shifted this distance, then division which is matching, the third one was matching, so third into list count. In this case, if the ninth one matches, ninth into 0.1. And we state it in a more general way. Yes. Okay, so what can we say? It's n into least count. So that is the distance shifted. Okay, that is the distance shifted. So somewhat like measurement, it is measurement. Okay, so we got what is this n? N is the matching division, or more properly known as coinciding division of Vernier scale. Remember this, that it is the coinciding division of the Vernier scale. Suppose in this case I matched 2 and 2, right? But it can be anything. Even the 2 can match with the 5 of the main scale. 2 can match with the 5 of the main scale. So what is the coinciding division in that case? Is it 2 or is it 5? It is 2, because we have to look for the coinciding division of the Vernier scale. So 2 of the Vernier scale matches with 5. So even if you don't pay attention at the main scale division, just check out for the coinciding division of the Vernier scale. Okay, so 2 matches with 5, 2 of the Vernier scale. So 2 is the coinciding division. Okay, so in this case I took it very special, like 1 matches with 1, 2 matches with 2, but it can be anything. Okay, 2 can match with 5, 2 can match with 9, anything. So you have to look for the coinciding division of the Vernier scale. List count, you already know how to find. 1 MSD minus 1 VSD. I told you the logic behind it. This is the minimum distance that your instrument can measure. But what if I say we are missing something in this formula, and that is the X factor, I'll say now. So I can remove this thing up. So quickly note it down. Okay. We are discussing a typical Vernier caliper, but we are getting the general results. So this is even true for generally for any Vernier calipers that holds this. Okay, so what is this X factor? What if I say my 0 of the Vernier scale was, now the Vernier scale is movable, you know that. So 0 of the Vernier scale has crossed, this is 3, okay, this is main scale reading is 3 over here, and it is 3.1, and then here comes 3.2. So it has crossed 3.1, and see, it has crossed 3.1. Other digits are also there. So 0, then 0.1, 0.2, till it has reached 3 centimeters, not millimeters. Okay, so it has reached 3 centimeter, and then we have 3.1, and it's between 3.1 and 3.2. Now I told you that the coinciding division is 3, so you got 3 into 0.1 is 0.3. So this is the distance shifted by the Vernier scale. So I told you that the coinciding division is 3, you take it as 3, and you know that the list count was 0.1. Okay, so 0.1 millimeters. Okay, now to tell it in the form of units, millimeters. So what was the distance shifted? Your distance shifted by the Vernier scale was 0.3, because the third one was matching. We are not worried about to which main scale division it is matching, since we want to know the division of the Vernier scale. So third Vernier scale division to list count, so is the distance shifted. But your Vernier scale came from all the way from 0 till 3, till 3.1, and then the shifting took place, right? It had to slide this distance first, this distance. So this distance is the X factor, okay? It had to slide this amount of distance, and then the shifting took place. So what I want to say is that measurement will be sliding plus shifting. So shifting, we already know how to calculate. It's n into list count, n into list count. So this hold for shifting, and this, the x factor, is for sliding. So how much distance it has slided, and then the shifting. Okay, the distance that it has slided. So you, how to calculate that, or how to look for it, is you check out for the zero of the Vernier scale. Okay, look for the zero of the Vernier scale. The entire scale is there. I'm not drawing it now. The zero of the Vernier scale, whatever number that it has crossed, zero has crossed 3.1. So 3.1 becomes your uh, the distance slided, or let's call it by the formal name that we use. It is called the main scale reading. So the x factor is nothing but main scale reading. Okay, so what we just discussed was measurement is the distance slided plus the shifting. Shifting, we already know, it's n into list count, so that much distance it shifts, right? So yeah, shifting we already know, but sliding, I told you how to calculate. So you look out for the zero of the Vernier caliper, zero of the Vernier scale, and then see what digit has it crossed. It has crossed 3.1. So our main scale reading in this particular example is 3.1, and it was centimeters, right? Yes. Okay, so measurement is sliding plus shifting. So so this is the perfect principle behind your Vernier calipers. So a small topic of zero error is remaining, but before that, you can quickly note this down. Now let us discuss about a zero error. So zero error is basically an instrumental error. So let's take an example first. See, if we have a weighing machine which measures 1 kg without you standing on it, it's just left for on its own and it's measuring 1 kg. So there is some instrumental error, we know it. Now you stand on it, it measures 61 kgs. But is your mass 61 kgs? No, it was measuring one extra, so you have to subtract that error, right? So your actual mass was 60 kgs, but it measured 61. So that is the same idea over here. So either your Vernier caliper will be measuring before we have actually started the measurement. So either it will measure something extra, or either it will measure something less. Like if I had to say your weighing machine measures minus 1 kg and your weight will be shown as 59, but actually it is 60, whatever. So that is just an analogy of explaining you what zero error is. First we'll take no zero error. So accordingly this formula will modify a bit, nothing much to worry, just a little difference. Here we'll take positive zero error, it's measuring more than what it's supposed to be, and negative zero, excuse me. Yes. So now what about no zero error? No zero error is in the case if both of the zeros of main scale and Vernier scale are coinciding. Okay, the zero of the main scale is coinciding with the zero of the Vernier scale, then it is then we call that Vernier caliper does not have a zero error. So if the zero of the main scale is coinciding with the zero of the Vernier scale, you use this formula, you'll get the answer. Okay, so what about now positive errors? What is so positive errors? So in positive error, this will be the case. So when you close, one more point, that you have to close your instrument. You are not supposed to measure, you have to close it and then check out if the zeros are coinciding or not. So if the zeros are coinciding, no error. And again you close your instrument. Now the claws are touching with the claws, and then you check. Now in such a case where the Vernier scale 0 is to the right of the main scale 0, the Vernier scale 0 is to the right of the main scale 0. This is movable, right? So it's to the right. So in such a case, when the claws are closed, if such is the case, then we call it a positive zero error. And how will you say, how will you measure it? It's basically shifting, if you can say. It's shifting, right? So how do you measure shifting? Is N into LC. So you have to look for the coinciding division on the vernier scale. So you first step is to close your instrument, don't measure anything. Then check out whether the zero of the main scale is coinciding with the zero of the vernier scale. If not, check it whether it's to the right or to the left. If it's to the right, the error is positive because it is measuring something extra, right? It is measuring something extra, so it is positive error. So okay, so positive error, so I'll put a positive sign here. So it's basically due to shifting. And how do you measure shifting? N into LC. So you look out for the coinciding division into list count will give you a positive zero error. Negative will be same, just a change in sign. So main scale 0, if you have here, and now you would have guessed it that vernier scale 0, if it's to the left hand side of the main scale 0, then we have a negative 0 error. Why? Because it is measuring something less. It is measuring something less. Okay. So quickly write that down, 0 error. This is negative, so minus sign, and it is due to shifting. So N into LC. So again, you have to look for the division which is coinciding when your instrument is closed, not measuring anything, and you look for the coinciding division of the vernier scale, and that into list count will give you the zero error. So what is the modification now? Where can I write it? So I'll write it here only, X. Suppose let's take the final measurement to be X, and your instrument has some zero error. So remember that zero error is always subtracted. Why is it so? Zero error is always subtracted. Okay. So this coinciding division and the one in the zero error may not be the same, because this is while measuring and this is while your instrument is closed. You would have got it now. So yes, so the final thing, the modification in the formula is minus zero error. If it's zero, it is the same formula. If it's positive, so if it's positive, so why did we subtract? That logic I'm giving you. So if it's positive, then finally it will be subtracted. You can see that if it's positive, it will remain negative over here. No. Okay. So it will be finally subtracted. So once you measure, and then your zero error, which was positive in this case, will be subtracted. So you will account for it. And if it's negative, this minus sign and this minus sign will make it positive, and it will be added. So this was measuring less, so we added zero error, and this was negative, this was measuring something more, so we subtracted the zero error. Okay. So zero error is always subtracted, but it might be positive or negative. So depends on the case. Finally, what happens to it? Like finally, in case of positive, finally it is subtracted. In case of negative, if you see, it is added, because it measures less, so you have to add. It measures more, so you have to subtract. Logic. Okay. Those who didn't get anything, okay, now you should know this. Those who didn't get anything, I'll just quickly brush up the formulas for you. Now let us quickly brush up the formulas. This is important for NEET people and BITSAT people. Just to remember the formulas, you don't have to go into the principle. JEE people, principle is important for you. Like the how the Vernier caliper works is important for you. Okay, so the first thing that we learned was list count is the difference between main scale division and Vernier scale division. Measurement is, so how do we measure using Vernier caliper? First is the main scale reading, how where your zero crosses Like we had this example 3.1, and here we had 3.2. So 3.1 plus the shifting. So this is shifting. So how you measure shifting is coinciding division into list count. So that is the amount of distance it had shifted. I gave you the feel as well. So coinciding division on the n is the coinciding division on the 1 year scale. We are not worried about the main scale, like whatever division it is on the main scale, we are not worried about it. We are just looking for the coinciding division of the 1 year scale. Okay, of, I'll write of the 1 year scale, of 1 year scale. Okay, so now this was perfect if it had no zero error. What if it has a zero error? Remember that zero error is always subtracted. Now once you plug in the value, then it changes. Like a positive zero error will be positive zero error will be subtracted and negative one will be added. But basically in general, zero error is always subtracted. Okay, so the formula for zero error in general, plus or minus, so it can be positive as well. In that case, the zero of the 1 year scale is towards the right. It can be negative as well, in which the zero is to the left hand side of the main scale. Okay, now what is this n? This n is the coinciding division of the 1 year scale, as usual, coinciding division of the 1 year scale when the claws are closed, when you are not measuring. Okay, so you have to close your instrument and then look out for the zero error. Don't just, you cannot look out it when you are measuring. Okay, you have to close it and then see whether there is zero error or not. Okay, let's clean this up. And time for problems. Okay, please note that down. It will be, this is the most important page, I'll say, of today's class for NEET and BITSAT people. Okay, so here is a question for you on the board. So it has asked you for the correct formula of least count if the n division n division of the 1 year scale coincides with n minus 1, and the nth division will be the last one. So that coincides with the n minus 1 of the main scale. So this condition already holds, though they have given, and they have said it is multiple correct. So quickly try it. Now I will try 1 2. Okay, so first one is this, obviously, since it's a general result for any 1 year caliper 99% of the time. Yes, and second one is D. Okay, why D, sir? Why, from where? Okay, so let's find that out. So they have said n Vernier scale divisions is equal to n minus 1 main scale divisions. Okay, so now quickly solve with this 1 year. So 1 year scale division, so I'm getting 1 in the form of other, so then I can then I will use this formula and derive one more. Okay, let's do that. So this, if we simplify, gives us this thing. Need to open the brackets, we'll open it in the list count formula. So list count in general, we know 1 MSD minus 1 VSD. So that gives us one main scale division will keep it the same, and 1 year scale division will express it in terms of the main scale 1. So 1 minus 1 upon n to main scale division. So 1 main scale division minus this into 1, so minus 1 main scale division, again this into that, so this minus and this minus gets plus, so main scale division upon n, or we can write it as 1 main scale division upon n. So this and this cancel, and what are we left with? 1 main scale division upon n. Now the school people might use direct this formula for your practicals, because they provide you calipers which are n division of whose nth division, the last one, we of the 1 year scale coincides with the second last of the main scale. Okay, so they directly provide use this formula, but the absolutely correct one is this. And for this caliper, 1 MSD upon, yeah, the D1, 1 MSD upon N. N was the last division of the Vernier scale, or basically the number of divisions, right? Last division will be also the number of divisions. 10 divisions, so 10th division will be the number of divisions. So if you want to remember this formula, you can, but remember that it applies only for n and n minus 1. So n Vernier scale division should coincide with n minus 1 main scale divisions. Okay. So I recommend you to remember this, because more than no 50% of the question will be this sort, n and n minus 1. Okay, 50%. 25% maybe give, you'll need to use this format, and nearly 24% you'll use this format, and the last one is VSD greater than MSD, which we are not going to discuss today. Okay, so let's go for the next question. I congratulations if you got this one. So here is the next question on the board. It says n divisions of the main scale coincides with n plus 1 divisions of the Vernier scale. If each main scale division, that is one main scale division, is a units, determine the least count. It may be multiple correct, and it's a JEE 2003 question, or rather an AI triple E question. Quickly try it. 1, 2, 3. Now I will do it. So first step I will do is to derive a relation between them, main scale divisions and Vernier scale divisions. So n main scale division is same as n plus 1 Vernier scale divisions. So yes, so one Vernier scale division will be n upon n plus 1 main scale divisions. Just got this over here. So yes, so we have found the relation between them. Now let's go for the least count, which says 1 main scale division. And if you say that condition is already held, since number of Vernier scale divisions is more, so it is less. So it is less in length. So one Vernier scale division is less than one main scale division. Okay. So one main scale division, what is that? A minus n upon n plus 1 into, here there is main scale division, so you can replace it by, so it is one main scale division. So one main scale division is nothing but a. So now can you sort it out? Yes, but I said it may be multiple correct, so there are actually two ways to look at it. You solve it further, you will get a into n plus 1 minus a n upon n plus 1. Now this an and this an will go, and finally you'll have a upon n plus 1. So option A is also correct. Now if you had to look it in the other way, you can use the previous question where we said the least count will be the smallest division on main scale divided by the number of divisions on Vernier scales. Now this holds for n and n minus 1. So it's like the same way, n and n minus 1, just it's framed a bit differently. So we have n main scale division and n plus 1. So it's like the same format. Here it's like n minus 1 plus 1, and here it is n. Okay, n minus 1. So n minus 1 on the main scale and n minus 1 plus 1 on the Vernier scale, or rather n. Not to confuse, you solve it further, you'll get the answer. So, or you can use that logic, the smallest division on the main scale divided by the number of divisions on the Vernier scale. That holds for only n and n minus 1. So n and n minus 1, it's the special case. Okay, so this was a JEE 2003 question. Let's go for the last question for the day. So here is the next question. It says it has given you the value of one main scale division. Vernier caliper has a least count this. This is the least count. N is the number of vernier scale divisions. M is the length of vernier scale. Length of vernier scale. Then you have to tell the value of N and M. So it's a single correct. Quickly try it. 1, 2, 3. Okay. Now it's easy, very easy. So they have provided the least count. So least count, you use the formula MSD minus VSD. So 1 VSD will be 1 MSD, which is 0.1 centimeters minus 0.02 centimeters. So this is like 10. 10 minus 2 is 8. So 0.08 centimeters. But what is one vernier scale division? Can we write it in terms of M and N? So where M is the length. So total length divided by the number of divisions. What does this give you? Can you think of it? Total length divided by the number of divisions. Won't it give you one vernier division? So the total length divided by the number of divisions, right? So if you have 10 millimeters and 10 number of division, so each division will be 1 millimeter. So how did you get that? So 10 millimeters was the length divided by 10 divisions, so each division will be 1 millimeter. So basically what you get is the length of one division, or what you get is one vernier scale division. So one vernier scale division. So now you already know it as 0.08 centimeters. So m by n should be 0.08. Now let's check the options. This will give us 0.05, wrong. This will give us m by n, no? So m by n, some non-terminating answer. So yes, that will be wrong as well. Recurring it will be. This will give us the correct answer. 0.8 divided by 10, 0.08. And here it will give us m by n 0.1, which is still wrong. So n is the correct one. It's very easy, right? Quickly note it down. It's easy. You would have done it by yourself. So that's it for today's class. So I will release one more question on the website, which will be our homework to you. Okay, so yeah, with that we finish today's lecture. So if you made it this far, please like the video and subscribe to my channel. We are just 9 subscribers away from hitting that 100. Go ahead and subscribe, and as usual, keep enjoying physics.